Now suppose some get tired and some eat an energy bar, okay? So they will change their speed. And so some will be faster, some will be slower. Then they will not all arrive at the same time. Some will arrive earlier and some will arrive later. Now that means that the total signal, which is a vector sum of the vectors pointing from the center to the bicycle rider, will be shorter. That means the echo will be attenuated if the bicycle riders change their speed while they are riding. Now that's important. If the bicycle riders don't change their speed, that would be the case where we have magnetic field inhomogeneity. One part of the sample has a higher field, the other one has a lower field, and the spins in that part stay where they are, and those in this part of the sample stay where they are. So the precession frequencies never change. That's static magnetic field inhomogeneity. That's the reason for signal attenuation, that is T2 star. It's a signal decay, and you can refocus completely. You get all the bicycle riders back when the spins stay at their position. But you don't get them back if the spins experience, for whatever reason, fluctuating magnetic fields. So something that at random changes. And why would magnetic change randomly for the spins? Well, because the molecules themselves move, they rotate, they're magnetically anisotropic. One molecule passes by another molecule that also has a magnetic field, and then you have, due to the motion of the molecules in the liquid or in the solid, you have fluctuating local magnetic fields that the spins see. So while they are precessing, they sometimes go faster and sometimes go slower. But that is completely at random. That is nothing predictable. So on the way this way and on the way returning, they see different fluctuating fields, and that means there still will be a spread of the bicycle riders at the finishing line, and the echo will be attenuated. And that, from the fluctuating fields, is the true T2. So what people would like to measure, they want to measure the true T2 without magnetic field inhomogeneity to learn about the local fluctuations of the magnetic field. Because that tells them about the mobility of the molecules, and a soft material will have higher molecular mobility than a rigid material. Or a high viscosity fluid will have lower molecular mobility than a low viscosity fluid. So T2 star, you can say immediately already with that, no, T2 will relate to the viscosity of a fluid. This is what the geophysicists exploit when they want to know what type of fluid is in my rock. Is it oil, or is it water, or is it methane? So they can use T2 for that. And again, also if, for instance, rubber are cross-linked macromolecules. If the cross-link density is high, then your rubber is very rigid, so it feels more like a solid. If the cross-link density is low, then your rubber is, you can stretch it easily, it's soft. And T2 scales with the cross-link density. In fact, that's something that the rubber industry uses when they produce car tires. They measure NMR to learn about the cross-link density locally in the car tire and optimize the vulcanization of the tire in the tire factory. At least in the R&D departments where they develop the procedures. And in fact, yeah, right. So this is hopefully explains the difference between T2 and T2 star. Repeat again, T2 star is what you have in inhomogeneous fields. You don't want to have it actually. And T2 is what you have in homogeneous fields or inhomogeneous fields, and it is solely due to the fluctuation of local magnetic fields from molecular motion. And there is the physics, it's the molecular motion. That's the physics part. And that is impacted by all kinds of things. You know, molecules sit in a small pore, they can move less freely than in a large pore. So pore size, you can measure in terms of diffusion, which we'll address later, by similar measurements that basically affect the magnetization decay and gives you pore size distributions, which you can nicely determine by NMR. That's something
So
correlator.
in normal spectrometers, it is possible to differentiate T2 and T2 star?
Oh, absolutely. You can do, if you can do an echo, you can discriminate T2 and T2 star. T2 would be, where am I? Here, difficulties with moving this. T2 star is the decay of the signal that you observe when you look at the free induction decay. But when you do an echo experiment and then change the echo time, then you observe the T2. T2 star is this one. And T2, where is it? Yeah, maybe this is a better example. If you measure the signal decay in an inhomogeneous field, badly shaped magnet, your signal decays fast, your line is broad. Then you see the blue decay. That's a T2 star decay. If your the magnet is perfectly shaped, very homogeneous field, you will see the T2 decay, which is long. But there may be still residual inhomogeneities which you can't shim out because, for whatever reason it doesn't work as well. Then you can do the multi-echo experiment, and that decay is the true T2 decay. There's still effects from diffusion in inhomogeneous fields that could enter if you have liquids. Then you have to take the echo time, that is the time TE between the echoes short enough, or the time between the 180-degree pulses, same, to make that short enough to have no contribution of diffusion to the relaxation signal. But again, this is part of a later lecture. So yes, you can measure that, and the relaxation is usually measured in terms of these of doing echo experiments and looking at the signal decay.
Then it is more liable to have T2 star.
Pardon?
T2 star, it is taking into consideration the inhomogeneity. T2 star.
Yes, that takes it consists of the true T2 and the field inhomogeneity contribution.
Yeah, so that means T2 star is actually the true value instead of T2 only.
No, you want to measure T2 because, or let's say most people want to measure T2 because that only depends on molecular mobility and motion. And people are asking, what is the mobility? That's the kind of physics aspect of matter, is the molecular mobility. The chemistry is really the chemical shielding, the J-coupling, and so on. And that you can resolve better when you, of course, have a shaped magnet and don't have much T2 stuff, only the true T2. So the line width is determined by true T2. Because that's explained here. When you do the Fourier transformation of these signals, then the red signal gives you a narrow line because it's long in the time domain, which means it's short